Hello students, welcome to the digital learning of session 7 of unit groups of BSc 3rd Sem Mathematics. I am Dr. Shashikala. In this session 7, let us discuss about definition and types of cosets and its properties.
Of the cosets. Any subgroup of a group gives rise to a Cartesian of the group into disjoint subsets. See here, the Cartesian of the group we have to remember, and it is a disjoint subset we have to remember. So if disjoint subsets are there of the Cartesian of the group, then that subgroup is called as a cosets. See, to clearly explain about the cosets, let us take the two types of the cosets, that is the right coset and the left cosets. Firstly, it is a right coset. Let G be a group and H be a subgroup of G. Then for any A belongs to G, then set HA, capital H, small a, which is equal to small h and capital small a, such that H belongs to H is a right coset of H determined by A. See, if it is the set is in this form, you have to remember very carefully here, and you have to understand this. Right coset and left cosets are important. So HA is equal to small h and A is called the right coset, which is determined by a. So let's take the example G is equal to -1, 1, minus I and I. And let's take the H as a subgroup of the cyclic group. So subgroup is taken as -1 and the 1. See, according to HA we have to consider. So H into I. See, here I have shown you. So what is your H elements? H elements are -1 and the 1. So -1 and the 1. We have to multiply this H with the I. So this becomes -1 into I becomes -I. Then 1 into I becomes the I here. So what happens here? -I, the set of the -I and I we got it. Nextly, see the elements of all the that is elements which is present in the group, we are multiplying with the subgroup of the cyclic group, that is H, 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 H. Here I, -I, 1 and -1, these elements from the group we have taken. So these element has to be multiplied by the H. So H into I becomes the -I into I. Then H into 1, again I have shown it here, H is -1 and the 1, it has to be multiplied by the 1 here, -1 into 1 becomes the -1, 1 into 1 becomes the 1. Nextly, H into -I, similarly as we have seen it here, 1 and -1 into here -1, it becomes the 1 and -1. Then H into -I becomes the I and -1. Thus, there are only two right coset H and HI of H in G. See, you have to observe here. So, what is this coset telling? Coset means disjoint sets. So, it is not a joint set. Disjoint sets we are telling about the coset. That means two disjoint sets we got it here. So, two disjoint sets are -1 and the 1. Then -I and the I. See, if you are taking a set here as -1 and the 1 and -I and the I, these are the two different sets. So -1 and 1 is present in H, -I and I is present in -I and the I. See, these are the two different cosets. See, if we are observing for I and -I, yes, here also I and -I we have, here also I and -I. But in the set G, we have -I firstly, then I as a second element. So this two elements is there only in H into I. Therefore, we have to consider H and the H into I. Not that. So here, that is, instead of H, we can also take it as a H into 1. So in these two sets, that is H into I and H into 1, so we got these two disjoint sets, the elements of the disjoint sets. So, but these two, if you are observing h into minus 1, we got it as a 1 and minus 1, but we want minus 1 and the 1. H into minus I is minus I and minus I, but we need to get minus I and the I. Therefore, we can't take these two. We can take these two. Therefore, these are the only two right coset H and HI of H in G. Nextly, the left coset. Let G be a group and H be a subgroup of G. Then for any A belongs to G, the set A into H. There it was H into A. Here it is A into H. In the left cosets, A into H we have to consider, which is equal to A into small h, where H belongs to H is a left coset of H determined by a. So let us take the group again minus 1, 1, I and minus I and the I. Then subgroup of the cyclic group H is equal to minus 1 and the 1. So as we have seen, it has to be in the form of A into H. So let us take the element. So I into H. So that is, we have to take all the elements from the group here. So I into H, 1 into H, minus 1 into H, minus I into H. So I, minus I, 1 and minus 1 is taken from the elements of the group only. So H is, we are taking as a minus 1 and the 1. So if we are multiplying, as we have seen in the right coset, I into the element of the minus 1, that is I into minus 1 is minus I into 1 becomes the I here. Then, so similarly for 1 into H, it becomes a minus 1 into 1, that is 1 into minus 1, then again 1 into minus 1, 1 into 1. 1 into minus 1 becomes the minus 1. 1 into 1 becomes the 1. Similarly for minus 1 into minus 1 becomes the 1. Then minus 1 into 1 becomes the minus 1. Then similarly minus I into minus 1, minus I into minus 1 becomes the I. Minus I into 1 becomes the minus I. So what are the two disjoints that we needed? We needed minus 1 and the 1, minus I and the I. So which are the sets we can consider? The sets are here this one, minus 1 and the 1, and I into H. These are the two sets we can consider for a 2 becomes the left cosets. So thus there are only two left cosets H and IH. See this one and this one. So minus I and I, minus 1 and the 1. But we can't go for these two because 1, minus 1 and 1. First element has to be minus 1. Second element has to be 1 here. But here it is, the first element is 1. Second element is a minus 1. So we can't consider these two. We can consider these two. That is H and minus I, minus H of H in a group. These are the two left cosets. Next is about the index. Let H be a subgroup of G. The index of H in G is a number of distinct right cosets of H in G. So it may be distinct left cosets or it may be the distinct right cosets of H in G. This is denoted by Ig of the H. So let's take the example here. Let G is equal to minus 1, 1, minus I. Then H is equal to minus 1 and the 1. Then index of H in G is 2. So here two elements are there. Since there are only two left cosets of H in G, only two elements are there. Left, right or the left cosets are two disjoint elements we have to consider. Minus 1 and the 1 we can consider. Again minus I and the I. So these are the two right cosets or the left cosets we can consider. So the index of the H in G is a 2 here. So that is, let G is equal to 1 minus 1 I minus I is a group here under the multiplication. So the subgroup of the G is considered as a minus 1 and the minus I, 1 and the minus 1 here is a subgroup of the G. So H into A. H into A form we are considering, we are going to get it as a 1 and minus 1. H into minus 1 and the 1. So H into I becomes I and minus I. H into minus I becomes the minus I and the I. So what we needed, 1 and minus 1 and I and minus I we needed. So if we are uniting these two, h1 and h1 and hi, so we are going to get it as a g here. So therefore the index of h in g is 2. So example, the next one is, if G is 1, minus 1, 2, minus 2 is a group with respect to the multiplication, and H is a subgroup, that is the elements are 1 and minus 1, then find out for a left coset of H in G. So G is, these are elements of the G, H, the elements are 1 and minus 1. So we have to find it for a left cosets here. So A into H form we have to write it. So what happens? 1 into H becomes 1 and minus 1. Minus 1 into H. So minus 1, H elements are 1 and minus 1. Minus 1 into 1, it becomes a minus 1. Minus 1 into minus 1 becomes the 1 here. Similarly for 2 into H, it becomes 2 and minus 2. Minus 2 into H becomes a minus 2 and the 2 here. So we can say these are the left cosides of the H in G. So this is in the form of A into H. So we are finding out the left cosides for all the elements which is present in the G. So this is 1, 1, minus 1, 2 and minus 2 from the group here. So H elements are 1 and minus 1. So these are the elements of the left cosets. So theorem 1. If H is a subgroup of the group G and if A and B belongs to G, then we have to prove it for HA is equal to HP if and only if A, B inverse belongs to H. So taking this, we have to prove it for this. Taking this, nextly, taking this, we have to prove it for this. Let us take this one and let us prove it for this one. So let us consider HA is equal to HB. That is, taking the LHS side, let us prove it for our RHS side. So let us consider HA is equal to HB, then prove that AB inverse belongs to H. So AB inverse belongs to H means it is belonging to the subgroup of the cyclic group. So there exists a element H and H dash which belongs to H such that let us take two elements. Let us take two elements H and H dash which is belonging to H only, where HA is equal to H dash B. So let us take it like this, because why we are taking HA is equal to H dash B, we are telling that HA is equal to HB. We are considering HA is equal to HB. These two are equal. So H and A are the two elements we are considering in the form of H and H dash. So therefore HA is equal to H dash B. Or we can say, so in the from the capital H, we are considering two elements H and H dash. Therefore, in place of capital H, let us take small h. In the place of again capital H, let us take the H dash. Then H inverse. Let's take one operation here. Let's take H inverse on both the sides. So group this. Group it for next step is grouping for H inverse into H becomes within the group. Group it for H inverse and H. So A is outside. Here group it for H inverse and H dash, and outside we have a B. So if you are observing this, so H dash into H, it's like 1 by H. So 1 by H into H becomes the E. E into A, which is equal to H inverse into H dash is as it is with the B. So E into A, this identity element with A becomes just a A. A is equal to H inverse H dash into B. Then see, actually we have to prove it for AB inverse belongs to H. So we got it A is equal to H inverse H dash B. Continuation. So operating for this element is operated with B inverse on both the sides. B inverse is operated on both the sides. Then AB inverse is equal to H inverse H dash. B and B inverse we can write it as a E. So identity element, this element becomes just H inverse into H dash. So A, B inverse as it is. So therefore if you are observing this AB inverse is belonging to H. Why it is belonging to H? So we are having an element of H inverse and H dash, this we got it from the H only. Therefore, AB inverse is belonging to H. So, taking HA is equal to HB, we proved it for AB inverse belongs to H. Next, conversely, we have to take this one and we have to prove it for this one. That is, AB inverse belonging to H, taking this, we have to prove it for HA is equal to HB. So, taking AB inverse belongings to H, we have to prove it for HA is equal to HB. So, HE is equal to HAB inverse. So, let us take it like this. So, HE is equal to HAB inverse. So, AB is equal to H into, that is taking operating B on both the sides. This is we are considering. This is the step taking as a now. So this taking this step, we are operating for the next steps. So taking or operating B on both the sides of this. So HB is equal to H into AB inverse into B. So HE into B becomes HB only because E is an identity element here. So next step is grouping for B inverse and B. So HA is outside the bracket. So nextly B inverse into B becomes a E. HB as it is. Then HA with the identity element E here. Therefore HB is equal to HA. So what we have proved, we proved it for HA is equal to HB. Taking AB inverse, we proved it for a HA is equal to HB. So therefore AB inverse belongs to H, which implies HA is equal to HB. So we proved it for if and only if condition here. Nextly for a theorem 2. If H is a subgroup of a group G, then any two right cosets of H in G are either identical or disjoint. Let AB belongs to G. Consider the right cosets HA and HB here. So if H is a subgroup of G, so any two right coset of H in G are either identical we have to prove or disjoint we have to prove it. So case 1, see either HA intersection HB is equal to pi. So we are considering, remember that it is a right cosets of the HA and HB we are considering, and the cases we have to prove it for what? We have to prove it for identical or the disjoint here. So therefore we have to prove it for HA intersection HB is equal to pi or HA intersection HB is not equal to pi. So let us take the first condition. Case 1, if HA intersection HB is equal to pi, so it is these two are disjoint only. These two are disjoint. So it is by default it is proved. So then HA and HB are disjoint only here, taking the first condition, that is HA intersection HB is equal to pi means what we wanted to prove as a disjoint, it is already proved by the default. Next, case 2 is taking HA intersection HB is not equal to pi. Then we have to prove it for is not equal to pi means it is proved for, it has to be proved for HA is equal to HB. So here HA intersection HB is not equal to pi we have to take, and is not equal to pi means it is proved it for HA is equal to HB. Suppose this is not equal to pi, that is HA intersection HB is not equal to pi, then there exists C belongs to HA intersection HB. Let's take one element C from this, that is HA intersection HB. In this, let us consider one element as a C. Then suppose X and Y belongs to H. So everywhere we are taking a subgroup only. From this subgroup, let us take the two element X and Y. So we have already said that we are taking C from the HA intersection HB. Therefore, C is taken as XA and C is already taken and also taken as a Y into B, because C is belonging to HA and C is also belonging to HB. Therefore, C is equal to HA, let us take C is equal to YB. Therefore, XA. So C equal to XA and C equal to YB. So we can equate these two, right? XA is equal to YB. Then operate for a X inverse on both the sides of this. So X inverse XA is equal to X inverse Y into B. So group for a X inverse into X with the associative law. Here group it for X inverse into Y. with the P. So x inverse into x becomes the E here with the A. So x inverse y into B. So E into A becomes just a which is equal to x inverse y into B. Nextly, for any P belongs to HA, P is equal to H into A, where H belongs to H, let us consider. And A is equal to, we have already considered for X, we have already taken for, or we have got it for A is equal to X inverse Y into B. That is only I am going to continue here. And also we have said P belongs to HA here. That is, we have to take the P as a H into A. Therefore, P is equal to HA. Let us operate. Let us take A is equal to X inverse Y into B. So taking this one, it is like now P is equal to HA. We are taking this step for the proving of the equation number 1 and 2. So considering PHA, how we are considering here? So we are taking for P belongs to HA, right? So from the HA, we are taking one element, that is from P, that is the P. So P is HA here. So where small h is belonging to H only. So P is equal to, so H x inverse into Y with B, where this is belonging to H into B, right? So associative law is considered. So here the bracket is for x inverse YB, here bracket is for H x inverse Y. Then therefore P belongs to H into B, where x inverse Y belonging to H only. So therefore P belongs to HA and P belongs to HB. Taking P belongs to HA, we got it the P belongs to HB here, right? So here HA, P belongs to HA and P belongs to HB. Taking P belongs to HA, we proved it for P belonging to HB. Therefore HA is a subset of the HB. Taking this, we got it for a HB. Therefore firstly HA is a subset of the HB. So call it as a equation number 1. Similarly, XA is equal to YB. So taking XA is equal to YB and Q belongs to HB. Firstly, we got it for P is equal to HA, right? P is belonging to HA, we got it. Nextly, we are taking a Q belongs to HB. So similarly, we are going to prove. So for equation number 1, we got it P is equal to HA. For equation number 2, we are taking Q is equal to H into B. So similar operation. So here H as it is, B is Y inverse, take the B value of the B we are taking as a Y inverse into X. As here we are taking the value of A as X inverse YB. In the second, to prove it for a second equation, we are taking B is equal to Y inverse. Here Y is there, here X is there, here taking B, here we are taking a Q. So in place of B, we are taking Y inverse X into Q, which is belonging to HA. Here it is belonging to HB. So taking Q belongs to HB, we got it for Q belongs to HA here. Taking HB element, we got it for a HA element. Therefore HB is subset of the HA. So in the equation number 1, you can observe HB in the right hand side. Here in the equation number 2, HB is in the left hand side. Here it is acting as a set, here it is acting as a subset. Therefore these two are equal. Therefore HA is equal to HB.